So I am Meredith Kenton, the Digital Marketing Specialist here at Megger. If you have any questions about webinars, feel free to reach out to me and I'd be happy to help you out. If you have questions during today's webinar, I ask that you submit them on the right-hand side of your screen. You should have a questions panel that looks like this one. At the end of the presentation, we'll try to get through as many questions as possible. If we don't get to yours, I'll make sure you get an answer via email after the presentation. And on that note, I would like to introduce you to our presenter today, Hein. If you want to take it away from here, it's all yours.
Yes, thank you. Thank you for the introduction, Meredith. My name is Hein Putter. The webinar of today will be about the maintenance of electrical components using online partial discharge tools. This will not only tell you how, but it will also go into detail what the benefits are, and will also explain you some basics about partial discharges, why they occur, what is the danger of having partial discharges, and how can we properly recognize them with what type of methods. As already mentioned, my name is Hein Putter. I am the product manager for testing and diagnostic products in Germany. So I'm located in Baunach, Germany, but I'm originally from the Netherlands, so the land of the cheese and tulips. Then moved in 2007 to Germany to join CBS KMT Megger. Started over there as a technical support engineer for the cable diagnostic products, and in 2011 took over the role of the product management for this specific area. I'm active in national and also international bodies such as the SIGRE, and my latest activities are in the SIGRE working group B158, which is about medium voltage cable asset management. If we have some questions later on, you can do that via the chat, or if you want to send me an email, that's also possible. I'm sure that the slides will be shared later on or will be seen on the link, so you can always send me an email if further details are needed. Before we start with the webinar, I first want to start with a video. So let's see if it functions. Looks good. Some of you probably already have seen this video. So this is if you look for explosions in electrical power plants, or if you look in substations, then this is one of the first videos which you see on YouTube. This basically shows a transformer where there was a short circuit and then oil came out, and then you have a nice big bang. And this is exactly what the utilities and what customers do not want to have in their network. So if you have an explosion like this, you can imagine that you have a long outage time, and repair costs will be high. You will have loss of supply, and if you are in an industry, you cannot produce. So these are things which you do not want to have in your network, and this is then basically the introduction of this webinar, as we are looking into tools which are focusing on the condition monitoring. The glossary. So I will first start with the boring part of the presentation, which is only a couple of slides. So don't go away. It's about the maintenance strategies. So there are a couple of maintenance strategies which you can apply. These will be discussed. Then I will go into the electrical details of the partial discharges. So what is PD? What are the consequences of partial discharges? How can we measure partial discharges? Then we are getting to the more interesting part, which is the overview of the methods for maintenance on MV and HV plants. So what methods are available and how to apply them and what are their benefits. And to get an all-around picture about the entire webinar, I'm ending with some case studies that you get a good feeling of how those tools can help you in your network environment. So there are several ways where it can support the network owners or industries or service contractors. Starting with the first slide, this is about the maintenance and repair strategies. In Germany, there is a nice document that describes all those maintenance and repair strategies. You can see it listed over there. It's a DIN VDE 0109. basically they list up 4 types of maintenance strategies, so how to maintain my network. The first one is the so-called preventive maintenance. So this is a scheduled maintenance and it's independent from the condition. So this could be a period of 3 years or 5 years where you are maintaining or checking your switchgear, or where you're putting some checkups of your substations. This is one generally applied method. Then the second one is the so-called event-based maintenance. So basically you do nothing until it explodes. So that's the video which you have seen before. So this is what I normally call the ticking time bomb. So hope that it doesn't fail, but if it fails, you can have a big problem, and then the costs can be far more expensive, or will be far more expensive compared to other maintenance strategies. And the latter two are both condition-based maintenance strategies. So speak, you do a measurement of your component, you have a report, and based on the report, you see how good or how bad that component is. And based on its condition, you are planning your new maintenance. So that could be in the beginning 10 years, and later on the period will become smaller. The good thing is you only measure when it's needed, so it depends on the condition. The bad thing is if you want to do your entire network, then you have lots of measurements to do. So that's why there's also the priority oriented maintenance strategy. That's the last one, which is discussed in this document. And this is basically only doing condition monitoring on the components with the highest priority. So where there is the highest risk of having larger outages, of having large outage costs, or having high costs of repair. So on those components you focus. On those ones you do the condition-based maintenance strategy. And on those which have a less or a lower priority, you can do a preventive or even the event-based maintenance. The advantage of the maintenance strategies is not only that you have an idea of how good or how bad your component is, but more important is that if you apply a proper maintenance strategy, is that you can extend the lifetime of your components. So you can keep things longer in service if you proactive repair or maintain components, such as oil field terminations. If the oil leaks out, you can refill them, then they will work out normal again. If you don't fill it up, it blows up, then you need to replace it. So this is just one example where you can see, okay, component can stay in service with just some simple oil fillets, or will break down if you don't perform maintenance on those type of assets. The longest lifetime you will get when applying the condition-based maintenance strategy, because over here you really have an overview of how good and how bad the components are, and you only perform action whenever needed. So this is the side benefit of applying a condition-based maintenance strategy on your network. One example is from Singapore. Singapore Power Grids, that's the network owner over there. They're using cutting-edge technologies for the condition monitoring for transformers, for switchgear, for cables. So they have lots of they have lots of diagnostic equipment to perform those measurements. And via that, they obtained a average interruption time per customer per year, so of only 30 seconds per year. And that's a very low value. If we compare that to Germany, where I'm now, then the average outage time is 10 to 15 minutes a year per customer. In the Netherlands, it's already 20 minutes. And if you go to other countries, it can be couples of hours, or in worst cases, even days per year. So the 30 seconds is almost nothing. And they achieve that via the measurements, but also via having remotely controlled switchgear. So that's not only one side, there are more things which they've used to reduce the downtime of their network. So before we continue with the PD part, I will first discuss the basic function of the electrical components. So we install, in this case, a switchgear. If it's installed, then it should stay in service for a specific lifetime. So normally 20 years, 30 years, could be 40 years. And after the end of the lifetime, it will be disassembled. During when it's installed, it should operate, so it should switch. It should withstand the voltage, so it should insulate. And of course, it should conduct the currents. And currents can be normal load currents, but must also be the short circuit currents, because this is a different stress for the components and they should withstand those short circuit currents as well. If there was no aging, then normally after installation, nothing would happen, and our switchgear would have a lifetime of 1,000 years. But unfortunately, we are not living in that era. Things are aging as of specific influences and therefore can break down. And one of the most important phenomena which causes breakdowns is as of partial discharges. So most of the breakdowns have PD in advance until they completely break down. And that's why this is one of the best early warning indicators. And that's where the main focus should be on for identifying issues in your network. Some images of consequences of partial discharges. So focusing on cables, you can have PD within your accessories, so in your terminations or joints. The one in the middle, it was already too late. So over here, the PD caused a breakdown. All the other ones, it's no breakdown yet, but you can already see the degradation of the partial discharges on polymer cables. And on the bottom side right, you can also see the electrical trimming on paper layers. This can be isolated bus bars, this can be within a transformer, or can also be a paper insulated cable. Fact is, there was PD, and finally, this will lead until a breakdown. In the HV world, things can be a bit more dangerous. So over here, you can see a VT blow up and also a termination blow up. These ones are made out of porcelain, and you can imagine if there is a blow up of your porcelain end termination or of your porcelain VT, if you stand close by, you can get injured, or other components also can get damaged. So preventing breakdowns in those components can save you a lot of money. Looking to switchgear or substations, over here the impact can be quite large. So if there's a fire within the ring main unit, this is a solar plant on the left-hand side there. They had a nice fire inside, and this solar plant is now out of service. So will cost money because they cannot deliver the energy to the grid. And if it's the utilities' fault, then they need to pay the money to the owner of the solar plant. So this is not what you want. The other two images are of larger substations where there are nice fires within the substation. They can lead to extensive damage or even of a complete renewal of your substation in case it's really broken down. So I know some cases from the UK where they had oil-filled switchgear, and if that blows up, you have the same like the introductory video. Then you have a big explosion, and then the complete construction of your housing will be gone. Last one, a bit smaller. This is a SF6 switchgear where just one simple termination blow up. The price of a replacement for a termination on itself will probably only be a couple of 100 euros, so not that expensive. But as you can see over here, it's not only a termination. Our complete cubicle, or looking to the upper part, 3 cubicles need replacement, and this then becomes expensive and will cause larger or longer outage times. So this is not what you want, especially within the switchgear. Breakdowns can cause massive damage. If you compare that to a joint failure, then you only need to replace a joint. If it's within a switchgear, it could mean that you either need to replace the entire station or the entire switchgear, or more than one termination. So this about the consequences of partial discharges. They can have devastating results which you not really want, and that's what you want to prevent, which can be when applying the online diagnostic tools. Now starting with PD, so what are partial discharges? There's a nice Bible written, which is called the IEC 6270. And within this Bible, it's clearly described what a PD is. And the first sentence describes it. It's a small electric spark that occurs at an insulation defect, but does not completely bridge the insulation. So it's not a flashover, because then you have a breakdown. It's only a partial discharge, which is only partially bridging the insulation. Those nice discharges in general are a consequence of the high electrical field stress. So it's not voltage dependent, it's field stress dependent. Can occur within the insulation or their surfaces. Luckily, they are accompanied by emission of sound, light, heat, and also chemical reactions. And this gives us a way to identify them. So we can measure PD because of those emissions. They can finally initiate a breakdown of the insulation. And if you look to a PD on an oscilloscope, then it's only a very short pulse with a duration of normally picoseconds or nanoseconds. So it's a very sharp pulse with a short duration time. The easy way, comparing it with an apple, it releases energy at locations where the R&D and or design engineers did not plan it, so it should not be there. It will cause decomposition of the material, so it will bite away your apple. It will reduce the life expectancy of your apple, so it will finally, there's no apple anymore. And in the end, you have a breakdown, there's nothing more to eat, all the material is gone, and we have a problem. Summarized, partial discharge is the predator of insulation. So this is not what you want to have in your network. PD is measured in coulomb or picocoulomb, depending on how high the discharges are. So normally picocoulomb, that basically is 1 ampere per second. For those who want to represent partial discharges or simulate partial discharges in MATLAB or PSpice, then you can basically represent a partial discharge by a classic ABC circuit. This is how it's written in the books. On the left-hand side, you see a insulation, and in the insulation, there's a void. This insulation represents a capacity, and the healthy part is the capacitance A. Then the part below and above the void is the capacity B. And the void is represented by a capacitance C with a spark gap in parallel to it. So what happens if you apply voltage to this circuit? Well, if you apply a voltage to capacitors, then they will charge up. If the voltage at capacity C becomes too high, then it will be higher than the breakdown voltage of the spark gap. Then we will have our flashover at our spark gap. The capacitor will discharge itself, and if the voltage is gone, the spark gap will go away, so will extinguish, and then the process starts from the beginning. Represented in a 60 Hertz power cycle, where Vc should be the voltage across the capacity, but as we have our spark gap in parallel to it, it does not reach the Vc. It breaks down whenever it reaches the breakdown voltage level of the cavity or of the spark gap. A discharge will take place, it will discharge itself, it will charge up, and so we get a repetitive pattern, as you can see on the right hand side. So there is not only one partial discharge pulse per cycle, you can have 10, it can also be 50 or 100, depending on the type of discharges which you have. So if you look to corona discharges, they are very intense and you have multiple, so quite a lot of them within one AC cycle. So that's the theoretical part. If we now go to a supermarket, then we can buy those discharges in several types. So there's not only one type of discharge, there are more. The most familiar one is the corona discharge. If you stand below an HV tower, a transmission tower, then if you hear a buzzing sound, that's the corona in air. So the discharge is in air. And this is basically a sharp point on high voltage potential, or can also be a sharp point on earth potential. Then we have the surface discharges. These are discharges on top of the surface. You can have PD as of delamination. You can have internal discharges caused by material imperfections. What also can occur is that you have PD as of a loose connection. So this is especially for test setups, but also if you want to earth something properly, then it needs to be earthed properly, because if you have a resistance in between it, or if you have a loose connection, then it will nicely spray and you have PD as of the loose connection. So also earth, very important. The last one, electrical trees are basically also PDs causing a electrical tree. So these are the typical partial discharge types, which you see when doing PD measurements. Looking to the causes for partial discharges, so why do they occur? They can have several reasons. It could be, first of all, a constructional issue. The manufacturers will always say, no, we've type tested our equipment, so it's not our equipment, but still this can happen. So they can oversee something, or there could be a bad batch of PTs or a bad batch of joints where they had some issues with it, and then it could be a constructional issue. Most common is as an assembly fault. So if workmanship is done, then you can do things wrong, and that can result in partial discharge. It could be a material defect, looking to casted potential transformers. There could be voids in the potential transformers leading to PD and in the end to a breakdown. You can have PD as of mechanical excessive stress. This is seen if you look to the elbows in the wind farms in the 36 kV rated, then sometimes you need to put an adapter inside to the elbow to close it. And if you put too much force on the adapter, you can basically break your elbow, or you can make a cut in the elbow, and that will then result in PD, and in the end, until a breakdown. Another cause for partial discharge is not directly from the beginning onwards, but in the later states, is a bad contact or a high contact resistance. So speak, you do not have a proper contact, then there is a high resistance. If there is a high load, then you will have heating or overheating, and the overheating causes accelerated aging, and in the end, the aging causes PD and a breakdown. So this is what we see quite often in wind farms, where load is normally high or higher than designed, and then we see that the accessories do fail as of overheating. If you look to air insulated components within a substation, you can have isolators, then moisture, condensation, and corrosion can cause PD. So this should not be forgotten. If you overstress your component, it's not designed for overstresses, so then in the end it will lead to PD and to a breakdown. And like us, components do age, so there will be a deterioration of the insulation, which can result to PD and finally to a breakdown. So as you can see, there's a long list of causes, and this is not all, so there are more, which can result to PD and not what we want. So now we know that there are several types of PD. We know that how PD can occur and what the causes are for partial discharges, but now we need to separate those types of PDs from each other. So there are corona discharges, there are internal discharges, and especially if you compare those two, then the internal PD is far more dangerous compared to corona PD. So how do we know if it is internal PD or if it's corona PD? Therefore, there are the so-called PRPD patterns. So that's a phase-resolved partial discharge pattern, which can give you some information about the type of weak spot which you have. In the first PRPD, so phase-resolved partial discharge pattern, you can see how corona looks like in gas, so it could be air. If the point is on high voltage potential, then it starts in a negative cycle. If the sharp point is on ground potential, then the PD start in the positive period. So already based on corona and in which period it starts, you know where you need to look for. If you have corona and oil, it's already a bit different, but still there is a separation. Then we have the cavity discharges. It could be a void which is bounded by an electrode. So it could be bounded by high voltage potential, or it could be bounded by earth potential. And then there is a difference in magnitude comparing to the positive and to the negative cycle. So that's how you can separate the cavity discharges which have one side bounded to an electrode. If it is internal PD, so to speak, it's in the middle of the insulation, then the magnitude of the partial discharges is more or less the same in the positive as well as in the negative power cycle. The last two ones are contact noise, bad contact. And if you've got a bad contact with high current, then you normally see that. So that's why the contact noise is seen at the voltage crossings where the current is normally the highest. And another typical PRPD pattern could be a floating potential, so something that is not earthed or not on high voltage potential, and then there is no specific phase reference, so that's not stable. It's moving through an entire AC cycle. This is then how you can identify floating discharges. Good. Now we know that there is a way to separate those partial discharges from each other via the PRPD patterns. Now we need to know how we can measure those partial discharges. For that, we have luckily the emissions, and as already mentioned in a bit earlier, the emissions can be electromagnetic waves. So electromagnetic waves can be light, heat, and radio waves. So light, it does some glimmering, so you can see it. It generates heat, which you can measure, and it also generates radio waves, which we can also couple out. The second way of emissions is acoustic. So partial discharges also creates sound, sometimes hearable by ear, then it's audio, sometimes not hearable by the human ear, then it's ultrasonic, but it generates an acoustic wave which can be measured. Last but not least, partial discharges also produce gases. Ozone, which you can nicely smell, but it also generates or creates nitrogen oxide. And if you combine the nitrogen oxide with moisture, you have nitric acid, and this is dangerous. So this will cause aging of your material. So if you've got this combined, so nitrogen oxide combined with moisture, this can cause aging of other components within, let's say, a switchgear cubicle. So material can completely be eaten away as of this. So that's why even corona discharges within an MV switchgear are not that not what you really want, because they can still cause damage to your components. So starting with the detection method, so how can we measure partial discharges and what components can be applied? Well, first of all, there is a nice man with a toolkit. He has a tool and he's got himself. So the human sense, we can also measure, or we can see PD. So we can see, hear, and smell PD. And these are the first 3 detection methods already. Other ways are via sound emission. And if you look to sound, this can be ultrasound measured via a acoustic sensor, or it can also be solid-borne sound. So speak, there's vibrations caused by the partial discharges, which we are coupling out using a piezoelectric sensor. So it's still acoustics, but measuring the vibrations, and that's the airborne sound. The optical spectrum, we have infrared cameras, which can measure partial discharges, or which can see or identify partial discharges. For the transmission lines, corona cameras are an option to identify PD during daylight. And the last one, which is the most common one, are the radio spectrum methods, where the first one is the conventional PD measurement using a coupling capacitor. We'll go into detail in the coming slides. Then there is an inductive way using high frequency current transformers. That's a clamp which you connect around your earth screen. Then there are capacitive ways, or also via ultra high frequencies. So in the radio spectrum, there are also several ways to measure partial discharges and to identify them. Before we start with the detection methods, I will first want to show you a slide about the battle online versus offline. If we talk about online, then we do not talk about an online PD measurement. We talk about online PD detection. So that's a big difference comparing to an offline measurement. What is better, online detection or offline measurement? I've listed it up over here. And if we look to the online detection, then the biggest advantage is, of course, you don't need to take your component out of service. So there is no work needed to de-energize your system to perform measurements on it. That are the first 3 points. The drawbacks of the online detection are that it's an uncalibrated detection of emissions. So especially if you look to acoustics, if you stand 1 meter away from the PD source, you will have a different result if you stand compared to standing 20 meters away from the PD source. So you can imagine that where you perform the measurements can already have an influence on the detection of the emissions. The other drawback is that especially the inception and extinction voltage cannot be identified or measured because you only have the normal operating voltage. A positive side is that in most cases you can localize the problem if you have parabolic receivers where you can pinpoint and then find the problem easier compared to conventional offline PD measurements. So going to the right-hand side of the table, if you perform offline PD measurements, then a high effort is needed to connect your system, so to do the setup. The system needs to be de-energized. If it's a cable, it's easy. If it's a larger switchgear composed out of, for example, 8 cubicles, then the complete 8 cubicles need to be disconnected from the grid. Then you can imagine that the time needed is longer. The big advantage is that we are now talking about a calibrated measurement, and we can now talk about picocoulomb. So we can measure the apparent charge in PC. In addition, we can determine all relevant parameters. So the level of discharges, the type of discharges, so the PRPD, and especially at which voltage does the PD start and at which voltage does the PD extinguish. So the PDIV is called the partial discharge inception voltage, and the PDEV, which is lower than the inception voltage, is called the partial discharge extinction voltage. I normally compare it with a relay. If you apply a voltage on a relay, then at a specific voltage, it will go on. If you decrease the voltage, then it remains on, and at a specific voltage, the relay goes off again. That's the same with PD. You need a higher voltage to initiate it and then a lower voltage to get rid of it. So having those online and offline methods, they both have their existence. So we both need them. Looking to the offline part, that's important for the installation. So if we install new equipment, we want to have a nice fingerprint. We want to have good assurance that the equipment has been set up perfectly, that there is no workmanship failure, and that can only properly be done using an offline PD measurement. So during the installation phase, the offline measurement has its right of existence. During the normal life cycle of the device under test, the online partial discharge detection is recommended because it's non-invasive, so you can easily apply it, you can measure, and if there are some specific problems with some components, then you can perform offline PD measurements again. So one example, on a specific type of VT installed in 1975, you had issues. On those ones, you want to perform a good assessment, then you can first start with online, or you can also do the offline assessment of those components, because you really want to have a proper reading of those components where you know that they already caused lots of breakdowns. Good, now going to the methods one by one. So this was the application strategy before, and if we now look to installation, then the conventional measurement is performed. And in this slide, you can see how such a typical offline PD measurement is performed on a switchgear. You have your normal external HV transformer, which is the power supply. You connect via a short cable to the switchgear, and then you do a test on your switchgear to test the bus bars, to test all the cubicles, to test all the PTs and CTs, and they should then be below a specific threshold level. In a IEC standard, it's clearly described how the PD diagnosis should be performed and how to perform the procedure. The normal procedure for switchgear in this case is that you first need to preload it with 1.3 times the UR, so the designed voltage of the switchgear. Then you need to go down to 1.1 times the designed voltage for the switchgear, and then measure for 60 seconds. And then during those 60 seconds, the PD should be below 20 picocoulomb for air-insulated switchgear without VTs connected, or 50 picocoulomb if there are VTs, PTs connected. If we look to gas-insulated switchgear like the slide before, then the level is only 5 picocoulomb. And in general, the PD inception voltage should be higher than the 1.1 times the operating voltage to have the level lower than 5 picocoulomb. So this is one procedure for after installation tests on switchgear and components within the switchgear, which are the bus bars, which are the PTs and CTs. And this is one way to properly assess the quality of workmanship. After things have been put into service, then the online detection stage starts. And over there are several ways available. I will now go into detail to the inductive, capacitive, and acoustic ways. So to detect PD on an electrical component, one needs to select the appropriate sensor. So unfortunately, there's not only one sensor which can detect all. You need to have a toolkit with a variety of sensors to be capable of completely assessing your component properly. Available decoupling methods are capacitive, so that's by means of a TEV, transient earth voltage. Could be acoustically, the sound. Could be inductively using HFCTs. This is commonly used for cables, or if you connect around the earth screen of the switchgear, you can also use it for switchgear PD. And a relatively new way, which I will further discuss in a separate slide is the capacitive coupling using the already existing and installed voltage detection system, so the VDS systems of MV switchgear. In the US, you don't have them in the manuals, but I can imagine that those ones are also installed within the wind farms or within the larger substations which we have, which show the presence of the voltage. Starting with the TEV sensor. So TEV are measuring transient earth voltages. The sensor itself you normally place on the outer surface of the switchgear cubicle. Could be a switchgear cubicle, could be a termination box of a motor, could be a termination box of the transformer. If PD occurs on the device of a test, it will induce a current on the metalwork, which will flow to earth. And this will, or this current causes TEV signals, which can be measured by the transducer. So as of the current flowing through earth to earth, we have a way to couple out the partial discharges. The typical procedure, if you are in a larger substation, you measure cubicle by cubicle. So from one to the other, not only on one position, but normally on at least 3 positions. First of all, where the elbows are, so cable input, then where you have your PTs or CTs connected, then where the circuit breaker is, and also on the bus bar side, you want to perform a TEV measurement. So that are the places where you typically have PD, and that's where you couple out. Now, like you see in this measurement, we had 5 smileys. So over there, everything is fine, but we have 2 sad faces and 1 very sad face. And this does not mean that we have 3 problems. With TEV, we have the issue, and that's the currents flow out or spread out to the other cabinets as well. So speak if there is one cabinet, like in this case, having high partial discharges, you also measure that on the neighboring cabinets. So that's why I always pay special attention if you do the TEV measurement. Don't say that you have 3 issues or 3 problems. If there's one with very high readings, then that's most probably the issue or the source of partial discharges, and the other ones is only the result of the spreading out of PD to the neighboring cabinets. Then we have the acoustic sensors. So if we look to the acoustics, then we need to separate or divide into structure-borne and airborne. Structure-borne is measuring the vibrations, like you can see on the right-hand side. So that are mechanical waves which we can convert into an electrical signal using a piezoelectric ceramic component. And why do we need those structure-borne sound sensors? Well, in this case, there is no air gap where the acoustic sound can go out of the cubicle, and then with airborne sound, there is no way to detect partial discharges. For that, we then need a contact probe or structure-borne sound measurement, like displayed in the image on the right-hand side. For those of you which are familiar with PD testing on HV-GIS systems, if you've got partial discharges within your GIS, then the localization is also done using those type of acoustic sensors. That's the same for transformers. If you want to pinpoint your PD within transformers, then normally acoustic sensors are used to pinpoint the issue. So they are coupling out the mechanical vibrations caused by the partial discharges. So they are very, very sensitive. For the airborne sensors, you need a direct coupling, of course. So either you need to have a direct access to a component, or there needs to be an air gap. And for that, there are several types of sensors available. The most common one is the parabolic receiver, like you know from surveying within a substation. You can measure corona and service discharges quite easily. And on the right-hand side, you see a flexible sensor where it's easier to go along the seams and gaps of the switchgear door to couple out the acoustic waves or ultrasonic waves which go out of those air gaps. And really, if there's PD inside, although it looks closed, if there's already a small air gap, the ultrasound still gets out, and it can still be measured using those type of sensors. Then PD detection using the high frequency current transformers. The principle itself is similar to a current transformer. There's a current flowing through the core of the sensor, which is generating or inducing a voltage, and the voltage we measure. And this is typically used for PD detection on cables and accessories. One utility in Southeast Asia, for example, uses the online tool with the HFCTs for pre-screening of the cable network to properly apply the offline PD measurement technology. So they have got thousands of cables, and They cannot perform offline measurements on all the cables. And now they use the online tools to find those cables having PD. And on those ones that have PD, they do the offline PD measurements to localize PD. In the US, you have your pad mount transformers. So over there, if it's possible, you can connect them around the earth screen and measure PD within the elbow and within the cable. Or if you have your manholes, then it's sometimes also possible to connect the HFCT around the earth screen and then perform measurements in the manhole itself. So this is a way to perform PD measurements to detect PD in accessories of the cable, such as terminations and joints, but can also be used on ring main units that you use it on the general earth of the switchgear or of the cubicle, and then identify the PD in the earth part. How do we apply it? So typically you connect the HFCT around the earth screen. An alternative could be that you connect it around the cable itself with the earth screen coupled back. But for this, you need to have a larger diameter of HFCT. So it can become complicated if you've got big cables. And the last one on the right-hand side, if you only connect it around the cable, then the HFCT makes no sense. Then you measure nothing. So this is not a way to detect PD. Applying the measurement, you connect around the earth screen, which needs to be accessible. So that could be one of the complications, or is one of the disadvantages of having of online PD on cables, is that in quite a lot of cases, it's not possible to connect the HFCT around the earth screen without energizing your switchgear. Especially in Europe, we have the compact switchgear. Then if you want to remove the lids of the cabinet, your cable needs to be de-energized, it needs to be earthed, and only then you're capable of opening the lid of your switchgear. And then you can connect your HFCT around the screen, which makes it then time consuming, and then you can already do an offline PD measurement as well. A workaround could be that you once install permanent HFCT sensors, which you couple out of the switchgear, and then you always have a way to access the switchgear cubicles. And another alternative will be discussed in the next slide. In this case, 3 cables have shown PD, and then depending on the magnitude of discharges, you can decide to perform offline PD measurements on one or all of those cables. The last way to measure PD within switchgear or on cables itself could be via the voltage detection system. So this is the CBS. Those ones are generally used to detect the presence or absence of voltage. So you can see it on the left-hand side. There's a nice high voltage sign, so that cable is energized. If you don't see it, it's not energized. But within this reading device, you have the banana plugs, and on the banana plugs, you can also connect your online detection tool. And via that, you have a non-invasive way to measure partial discharges within your switchgear cabinet. Those capacitive sensors are normally the boosting adapters of your switchgear cubicles. So they are ideally located because they are on one side directly within the switchgear, on the other side directly on the elbow. So you can get very accurate readings with it. It's not applicable on all types of VDS systems, especially the older ones. It could be that it's not functioning. So I cannot say that it will work on all VDS systems, but we've done quite a lot of work and measurements in the field, and we've seen that on most of the VDS systems which are installed, this way of coupling is also functioning. So then the last way of measuring partial discharges is then via the optical spectrum. These are alternative PD detection methods. Starting from the right-hand side, we have the infrared camera. So if there is partial discharges, it generates a heat. And if the heat is that high, then it can sometimes be detected using infrared cameras. On the right-hand side, it's a termination having PD, and the hotspot is seen on the infrared camera. Then we have the corona cameras. They are used in the HV substations or for transmission lines. You can see the PD then in daylight. Whereas during nightlight, you can see them, during night, you can see them with your eyes as well, but during daytime, you can then see them with a corona camera. And quite recently, there are also acoustic cameras on the market, which were designed to detect leaks in pipes. But they also did some measurements in substations, and I've seen that also discharges can be identified using those acoustic cameras. So how sensitive they are, I cannot tell you, but this is another detection method to measure or to detect PD. So finalizing with the case studies, so that you have a better feeling of how to apply those methods and what type of benefits you can have from it. This is from a power utility in Germany, from Westnet, where I used this example from. They had a failure within their switchgear. There was a short circuit or a three-phase short circuit on the switchgear. And the root cause of the issue was a defective potential transformer. And this became defective because there was measured between two phases, and they had aging of the isolating surface, so surface discharges on top of the potential transformers. As they have identified the root cause, they performed an inspection in the entire substation via ultrasound, and they have identified other potential transformers having PD, and those ones have been preventively been replaced, and there no problem will occur anymore. So this is over here, the root cause was a breakdown. They found the result of breakdown, analyzed other components within the same substation, found other components which have PD, replaced them, and then life is okay now. In a second case study, it's PD detection on a ring main unit or on a ped mount transformer. It could be the same. During the routine inspection, they also performed unconventional PD detection. Anomalies have been found on the housing of the switchgear. Then they've localized via visual inspection, and they've recognized that there was a defect on the cable going from the switchgear to the transformer, so the transformer feeder, which could have caused potential damage to the entire switchgear cabinet. So this, on the right-hand side where you can see the arrow, that's where the PD occurred. And the white markings, which you see on the brownish material, that's already caused by partial discharges. So that's what you sometimes see on elbows. If they have surface discharges, then there is the white dust that's caused by partial discharges. Then the last one over here, this was a measurement on a VDS system. This was maintenance performed in a wind farm where there were 16 wind turbines connected to it. So there's a 36 kV switchgear on the feeder cable. So really important, because if the feeder cable breaks down, then loss of supply. Same with the switchgear cubicles. If it breaks down, loss of supply, loss of money. So they performed an online detection, and on all those switchgear cubicles, they could not measure any PD using the TEV or acoustic method. But using the VDS, they measured PD on one switchgear cubicle. So as TEV and acoustic didn't show any PD, the VDS did show PD. The PD must come from the cable. And in the end, the recommendation was to perform an offline PD measurement on the cable. This is what they have done, and this is how it's represented in this graph. For those of you which are not familiar with offline PD measurements on cables, on the x-axis, you can see the cable length, and this was a relatively long cable of 45,000 feet, so 15 kilometers. And on the y-axis, you have the partial discharge height, so the level of PD. And over here, PD has been identified in two phases, whereas red was phase A and blue was phase C. And on those positions, there were joints which now have been replaced. So online detection recognized PD on the switchgear, was not the switchgear, was the cable. They performed an offline measurement during a scheduled outage. So if you measure PD within a cable, it doesn't mean that you need to measure tomorrow to replace. You have time to schedule your measurement. So they performed the measurement during a scheduled outage of the wind farm. They did the detection and the localization and could replace the joints then when the wind farm was in a scheduled outage. So no additional costs involved. So summarized, I've now shown quite a lot of ways to measure PD. And the main reason why we perform this is to perform condition monitoring on assets. And this extends, or by applying this properly, you can extend your maintenance intervals. You can prevent failures from happening. You improve safety. So safety is a very important point. So in the UK, this is the most important point. So they perform detection within the substations as of safety issues, as they have quite a lot of oil field switchgear in the network left. If there is a breakdown in the switchgear, it can cause a big blow up and then people can get killed. So that's why in those substations having oil field switchgear, PD detection needs to be performed before entry. When applying condition monitoring properly, you will decrease costs, you will reduce the capital expenditure and also supply. And in the end, you can properly manage your maintenance, refurbishment, and replacement. So these are the benefits of applying condition monitoring using online PD tools or detection tools such as cameras. Partial discharges are the main cause of failure, so that's why this is the most important one to monitor. There are several ways available to measure PD, with each having its typical application and advantage. So there's not only one way to detect PD, there are more ways to detect PD. And that's why you need a bigger toolkit, but most online tools combine those already. So I will end my presentation also with a video. Online PD detection does not prevent from idiotic failure. So over here, you can see a video of where they left the system earthed and then energized it. If you still do this, or if you do it within a switchgear cubicle, then you can still have a big blow up. Although applying online detection, those faults can still occur, but this is because of idiotic actions. So I hope you found this webinar interesting. And I would be delighted if you have some questions which we can go, or which we can discuss now or later on per email.
Okay, I think we probably can squeeze in a few questions if you have the time. The first question we got is, can the TEV sensor be used for any medium voltage switchgear design, even metal clad or metal enclosed?
No, so like mentioned, the TEV, so to detect PD, you need to have a range of sensors, and the TEV sensor cannot identify all PD. So there are, if there's, for example, a bad capacitive coupling to the metallic surface, then you do not identify the PD using a TEV sensor, but you can identify them using a acoustic sensor. So the TEV will not detect all types of PD. You need a combination of them, and it also depends on the type of switchgear you have. So you need to have some opening where the signals can go to the outer surface of your cabinet.
Okay. Is an arc flash a type of partial discharge?
If I understand an arc flash properly, then it basically completely bridges the insulation. Then it's normally a breakdown which extinguishes itself again. So I would say an arc flash is not a PD. It's a short breakdown. No?
Okay. Okay, let's try to get through a couple more. What is the minimum voltage of the switchgear or switchboard to detect PD with the TEV sensor?
So it's not voltage dependent. So partial discharge is depending on the electrical field. So even with 1 kV, you can already have a very high field that PD can occur. So the general types of switchgear start at 1 kV and higher. So 3 kV or 6 kV. Over there, the TEV sensor already works. So it depends on the electrical field and not on the voltage. But from that range onwards already. No?
Okay. And then let's just do one more and we'll get through the rest via email. But how can I eliminate Oh, sorry, I read the wrong one. What is the minimum voltage for PD detection where breaker contact resistance is high?
Yeah, so I slightly touched it with the causes for partial discharges. So if the breaker resistance is too high, it generates heat, and the heat can cause then the aging of the material around it. And if the material is aged that far, as of the overheating, then until PD occurs, then PD can be detected. In the beginning stage, if you have a high contact resistance and if it has seen no load, then there is no PD. So it basically depends on the status of aging caused by the overheating of the bed contact.
Okay. And I think we're out of time. We ran over a little bit, but we will get through the rest of the questions via email. So thank you, Hein, for your time, and thank you everyone so much for attending.
Also, thanks from my side for participating, and I'm looking forward to some more questions which I will answer and which you will hear from us.
Perfect. Have a great day, everyone.